Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are now on our 11th lecture. So far we have discussed about contact without adhesion, concentrated and distributed load on an elastic half space, plane strain approximation, uniformly and spatially varying distributed load, and stress components at a point inside a elastic half space. We are now discussing the deformation on the surface of this elastic half space because of this linearly varying load that we started in the last lecture. So, today I will like to finish off and then we will start in another lecture, another topic, that is axi-symmetric normal load applied on an elastic half space. So, remember in the last lecture I derived this expression of del v by del x, that is the gradient of vertical deformation at the surface of this elastic half space that is subjected to this kind of linearly varying loads and where this particular load can be written as P is equal to P 0 by A into A minus S like this, and this is a distance at S like that, and this is at x. So, we used all that the detailed derivation I had done, and now we will derive what is V here, and that for that we will use this particular integration result. And here if I integrate it and use that, so we will have, instead of for x ln of x is equal to this term x square by 2 ln of x minus x square by 4, and into this is a plus x ln x plus a. Instead of x we replace a plus x. So, it will be a plus x whole square by 2 ln a plus x minus a plus x whole square by 4, and like that. And with an integration constant, this is c. C has to be found out by writing that this v at z is equal to 0 will be 0 at a very large value of x. And then we do little manipulation, algebraic manipulation, and we get finally this expression which comes out very naturally over here. So, like that we can get, and we can write down this expression a little differently, and so that we can have here ln of a plus x by somewhat differently. So, this is a plus x whole square. So, I would like to get here let us say ln of a plus x by ln of a. So, in order to get that we had added some terms and subtracted our some terms. So, for example, over here I had written here minus a plus x whole square ln of a, and for this term I have written here minus x minus a whole square ln of a. And if I add both these terms, I will see that I have to, this is a subtraction over here. So, I have to add this particular term over here. So, we do all that. So, this is just to write the result in somewhat more organized manner, that is it. Otherwise, this result that you have derived is good enough. It is like that. So, now the moot question is that how does this deformation profile that looks like as a function of x, or rather what kind of indenter will give rise to that linear normal load on the surface. So, that is what is the question. Before that, del u by del x can also be written over here, and here if you just add up, it will be minus, and here it 1 plus sigma by 1 minus 2 sigma, 1 plus sigma into 1 minus 2 sigma, and by E, and this will be equal to P 0 by A, and here it will be A of x minus this will be x square by 2 here, and so here it will be like that, and where x is greater less than equal to A, and if x is let us say at a point outside, if the point lies outside the region, outside the loaded region, the u will be come out to be something like this, which can easily come out. So, it is like that. So, now what kind of indenter will give this kind of vertical deformation, that is the question. So, we can actually find it out by from this expression that and that particular indenter will look something like this, and this is the profile that this profile captures this equation here, and when this kind of profile is expected to give this kind of linear distribution of load on this elastic half space. So, remember that we are considering the case in which there is no adhesion and there is no friction between this indenter and this elastic half space. So, this dotted line is the undeformed surface of the elastic half space, and you apply some amount of load here. So, that is capital P here, let us say, and so the load distribution will turn out to be something like this. Now, suppose if I think that the load distribution is opposite, in the sense that let us say that that there is an adhesion between this indenter and this indenter surface and this elastic half space, and then we are trying to pull it off. So, you are first brought it in, I have first brought in contact this load, and then let us say that this indenter, and now let us say I am trying to separate it. So, in that case let us say that I am looking for an indenter shape that will give rise to normal load once again. So, it will look something like this, the load distribution. So, let us say the maximum load is at x is equal to 0 here, okay, and then it is something like this, the load distribution something like that. So, in that particular case, okay, what will be the deformation profile, and following that what is the indenter shape, basically that we are looking at. So, it is it will be something like this. With adhesion, the indenter shape, this film, okay, or this elastic half space, this elastic half space is supposed to deform, okay, something like this, and when it happens that, and that can happen for a rigid indenter which has the shape of this particular form. So, this kind of indenter, let us say I first bring it in contact with this particular elastic half space, and there is a adhesion between them, and now let us say I try to pull it. So, when I pull it, and then say since there is a sufficient adhesion, so there is no debonding that happens, okay, this material then as I pull it, so the force will look the pulling load and will look distribution will be something like this. Now, why it is interesting, because notice that in this case at this particular edge, so that means over here the load the stress is actually equal to 0, it will be tensile stress, but it is actually equal to 0, and it is maximum tensile at this point. So, therefore, in this particular case, if we want to say that there is a debonding occur between this indenter and this half space occurs. So, this debonding will not start from this edge, but it will start from somewhere inside, or rather at this particular point where the tensile stress will be maximum. Contrast this with this particular distribution that we had discussed in before some time back, a few lectures back, and there this is the kind of profile, the vertical displacement profile that I will get from, and that will lead to this kind of uniform distribution, okay. In this, of course, all these problems are being solved in plane strain approximation, that is in y direction, that we have done shown here. So, here it will look so basically here the indenter is something like this, like this, okay. So, now here the load distribution will be uniform like this, and again if this is without adhesion, this is without adhesion, but if we consider adhesion like here, then if I think that what kind of normal what kind of indenter will lead to this kind of normal distribution of the load. So, the indenter has to be of this particular form, because indenter is rigid indenter, remember that, and suppose there is sufficient amount of adhesion and we first bring it in contact and then we try to pull it, and we are pull by applying some load, then in that case the deformation will be something like this. And over here, however, just see that at this edge, okay, there is a finite tensile stress. Of course, this is tensile stress, and tensile stress is uniform everywhere. So, as a result, in this particular case the debonding may start, okay, anywhere, it can start in the edge or it can start somewhere inside, as well. So, the debonding pattern, when you consider the adhesion, we have not yet started considering adhesion, but when you start considering adhesion, the debonding pattern will depend a lot on the shape of the indenter or shape of the contactor, and of course, it will also depend upon the modulus that see he is here. So, the modulus, it will depend upon the modulus, elastic modulus of this material, and the adhesion we have not considered yet. So, this adhesion between this, because if the adhesion is low, then at small small amount of displacement itself, this there will be demanding. So, we will take it up that adhesion problem okay, little later. So, that is all I wanted to say about this line load and distributed load in the plane strain approximation. So, today we will continue our discussion on contact mechanics by considering this what is known as the axis-symmetric loading of an elastic half space. So, in essence, elastic half space you already know that this is z towards z direction is infinity, and this is x direction also infinity, x direction was minus x direction infinity. Only thing is that it is bounded by this plane, that is z is equal to 0, and let us say there is a point load that is being applied, concentrated normal point load, that is P is being applied. So, what we are interested in is that suppose there is a point inside the elastic space here, which is at a distance rho from this point of application of the load, which boils down to in this coordinate r theta z, let us say that it is theta symmetric, and in the r theta z symmetry, it is r distance from this z axis and z distance from the this is r axis or x axis over here, okay, x axis over, let us say. So, at this particular point, what are the stresses that is developing, okay, and then we can find out that what are the kind of deformation that is there, and then if this particular point goes to the surface, but that is at v at z is equal to 0, then what is the deformation there. So, that is the kind of question that we can find out, and we can follow the process, the solution process very similar to the one that we had done earlier. And remember that in earlier in the case of line loading, okay, we had changed the coordinates, we had solved actually the coordinate in the r theta axis, but here we can do it when r rho and phi and all that. So, I am not going to go into that detail, okay. However, I will like to say that we can find it out in r and theta coordinate, and finally, we can get the expression for the normal loads Gz and Rz, okay, which is written here, okay, Rz and Zz in this way. And we are mainly interested in the displacements. So, the displacement components can be written like that. I have already defined what is rho here and r here and the z here. I have already defined that. So, we already have it. So, basically this. Now, we want to we are mainly interested again at z is equal to 0, that is at the what is the displacements or deformation, same thing, okay, at the surface of this particular elastic half space at which z is equal to 0 here, and that you can easily write u is equal to, this is p by 4 pi mu, and this is z is equal to 0 here. So, that goes, it is minus 1 minus 2 sigma, and remember that is minus here, minus minus plus no, z is equal to 0. So, minus should be here, and then rho by rho. So, it is 1 upon r, okay, like that, and v will be equal to capital P by 4 pi mu, and z is equal to 0 here. So, we do not worry about it, and rho will become equal to r, okay, because here if you see here, if this particular point goes to at the surface, then this rho will be equal to r here, and so therefore, over here it will be 2 into 1 minus 2 into 1 minus sigma by r. So, it is like that. So, mu is the shear modulus and sigma is the Poisson ratio, and this is u at z is equal to 0 and v at z is equal to 0. This is the vertical deformation or displacement at the surface of this elastic half space, and u is the horizontal displacement or deformation. So, it is like that. So, now what we know that this is the that was for the point load, but let us say that we will consider now a distributed load, and the distributed load is over a circle. So, this is the surface S on which there is a circular area of radius a, let us say. So, let us say this is the radius a. So, on this surface some load has been applied. So, we want to know that what will be the deformation profiles, okay, on this because of this application of the load, normal load, shear load, okay, pure distribution is Px here and Qx and Qy here. So, Qx is the shear load along the x direction and Qy is the shear load along the y direction. So, let us say that this is the particular point where let us say that this is the P xy, that is the normal load applied, and then Qx, it is Qx over here, this is Qx and this is Qy. So, this is Qy over here, like this. And because of this application of the load, okay, at this particular point, what is the displacement at some other point, let us say this point. So, let us say that this point is C represented by C here, this point is represented by B here, but actually this the loads the stresses can be found out at this point, which is vertically below this particular point B. Let us say this is point particular A. So, we can do all that, and we can use the superposition principle to find out that what will be the total stress, normal stress at this particular point in the x direction, y direction, z direction, all that we can do all that. But for our purpose, we are interested in finding out the deformation at this particular point because of the loads which have been applied on this area. And in order to do that, okay, what we will do is very simple. We will consider that, let us say that our origin is at this point and the load has been applied over here. So, we will consider that this distance as S, and let us say this is the perpendicular distance to it, like that. So, so here this we will consider that this S is this particular point. So, this is the B point which is at x y, let us say, and at the C the loads have been applied, and we will consider only the normal load. So, let us not worry about this q x and q y over here, and we are considering at the surface only. So, like this. So, from here we have a so here these are the axes. So, this particular B point is actually at a distance r from this center, and so and perpendicular to that this is the perpendicular direction to this, this is the direction. So, from here this direction there is an angle phi here. Okay. So, what we think that this is the distance from B point to C point, that is S here, and we can think of a small strip over here. Okay. This is d phi into S. So, this is d phi here, this angle. So, consider this is d phi here, and so if I magnify this, it will be something like this. So, this is let us say something like that, something like this. So, here this distance is d s and this distance is S d phi, this is S d phi, like that. So, let us say the load that has been area applied on this area now will be given as P into S into ds into d phi. So, this is the area and the P is the area load per unit area, okay, the pressure that is being applied, compressive load pressure that is applied. So, therefore, the load that has been applied here is P s ds d phi, and therefore, this is the point load over here, and so because of this load, what is the displacement or deformation at this particular point. So, this is infinitesimal area. So, I should write here dV here, this infinitesimal area, and therefore, this P can be replaced by this P s ds d phi, okay. And we already have this expression, as you can see this expression, okay. Here this R will be replaced by S. So, here R is replaced by this quantity S here, okay, and P is replaced by like this. So, this is the differential vertical displacement at this particular point B because of this small the force, the P that has been applied over an area infinitesimal area, okay, at this particular point C. So, this is the quantity. Now, we need to integrate this quantity in order to find out the vertical displacement V because of this load that has been applied whole through this area, and that is what we are going to do now for different cases. So, here we have already done that. Now, what happens is that what happens is, let me go back, let me go here, yeah. So, now we can integrate. So, this S and this S gets cancelled over here. So, finally, we have this expression, okay. So, we have to integrate and we have to find out that the region with which S varies and the phi is the angle. Now, in because of this softwares, okay, this angle phi, okay, it is actually equal, is the same as this represent phi. So, this happened because of this Mathematica or math mode that we used. The font changed somewhat, but please do not get confused. This phi and this more font, and then these are basically same over here. So, So, it is like that. So, yeah. So, therefore, there is no reason to get confused. So, it is like this. Now, this is the general formula, okay, which will be used for various pressure distributions. So, the first pressure distribution that we will consider is, let us say, uniform pressure P0 applied whole through this area. So, therefore, this V we can find out now will be, so now before that. So, whole through the apply. So, now we want to find out, let us say, this particular point B here, this is at a distance r and it is, let us say, 0. So, at a distance r from this center, and let us say that there is another point C, the load infinitesimal area is over here, and let us say that this point C is at a distance let us say t from here, and this is the point B here. So, this is the line. So, this line is, let us say, S, the distance is S, let us say, and as I did earlier, so there is a infinitesimal area here. So, this area is given by this is the point C here. So, the area here is, so this angle is phi here, and so this angle is d phi here, and this area is S d phi and ds, like that. Okay. So, what we are saying is that what is the deformation at this particular point B because of the load that has been applied and in this area, that is what we want to do. And this point is at a distance t from here, and so this is so yeah. So, now apply from the center. So, its situation looks something like this. So, the force that is exerted on this area will be P0 into ds into d phi into S, and so therefore, the net deformation at B will be written as like this. So, this is directly from what we had derived a little earlier. So, it is something like this. Now, here you can see that for a given value of phi, okay, this is constant, P0 is constant. So, for a given value of phi, the S, I mean this quantity is S. So, we want to integrate over the whole area. So, for a given value of phi, the S varies from, let us say, this distance, let us say this is S2 and this is S1. So, this is from S to S1. So, if we integrate over phi from 0 to pi, okay, A0 to pi, then we will actually cover the whole area for this particular case. Okay. So, here for a given phi, S will vary from S will vary with phi by S will vary from, let us say, S2 to S1 or S1 to S2, whatever, and the phi will vary from 0 to pi. Okay. So, the phi has to be varied from 0 to pi, and that will cover basically the whole area. So, how do I define, how do I find out S? That is the question here. So, that can be easily found out by solving this following equation. So, let us say that we need to find out what is this distance S here. So, let us say that yeah, so this distance. So, let us say that this distance. So, you know that this area, this radius of this contact area is A, it is written here. So, the A square. So, A square, okay, is equal to R plus this is S, this distance is S here, as this is phi here. So, S cos phi, okay, whole square plus this is S sin phi, S sin phi is this will be this distance, right. So, it is S sin phi square. So, this is the equation is like this. So, if I expand it, it will be R square plus S square plus 2 R S cos phi. So, what it means? Let us say I write it differently, S square plus 2 R S cos phi plus R square minus S square is equal to 0. So, if I solve, this is a quadratic with respect to x and I can solve it. So, here S will be equal to, therefore, minus 2 R cos phi plus minus square root of, this is b square minus 4. So, it is 4 R square cos square phi minus 4 into R square minus S square by 2, like this. So, 2 gets cancelled over here. So, it will be minus of r cos phi plus minus this is r square cos square phi, this is plus a square. So, it is a square here and minus r square sin square phi, that is what it comes out. So, S12 S1. So, S I have got two values minus r cos phi plus square root of a square minus 4 sin a square minus r square sin square phi, and S another value is minus r cos phi and minus of this quantity. So, here this S12 has got these two values, and so we substitute that. So, now if we integrate it with respect to S, okay, we will get therefore S2 minus S1. So, here S2 minus S1, let us say that will be equal to, okay, from here we can directly see this quantity will be equal to whatever we get here. So, this is S2 minus S1. So, it will be let us say square root of A square root of A square minus r square sin square phi, and it has to be multiplied by 2 here, right. From here if we do S2 minus S1, so it will be like that. So, therefore, that is what has been substituted put here, and now we can need to find out this integration where phi varies from 0 to pi. I just defined why it is like that. So, here this 0 to pi. So, what one does is this is sin square pi phi. So, one can actually integrate from 0 to pi by 2 multiplied by 2 here. So, therefore, it gets here 4 here and 0 to pi by 2, and one can get finally this particular integration. So, it seems that this particular integral does not have any analytical form, but it is called what is known as elliptic integral. Okay. So, here this is the coefficient term and this quantity is called the elliptic integral of the second kind with modulus r by a. So, this integral, as I said, okay, it does not have any analytical solution. So, it is a series solution that one gets, and this is called the elliptic integral, and integral is called complete elliptic integral because integration is being done from between 0 to pi by 2. If it is being done even less than that, then it will be incomplete, but it is completely integral over here. So, one can find out numerically what will be these values, and one get here elliptic integral will be get something like this. So, at r is equal to r by is equal to 1 or r is equal to a here, that means its modulus is equal to 1, this value is 1, and at 0 this is pi, it is like it is 1 pi by 2, it is like that. So, therefore, one can get here integration being done between 0 to pi by 2. So, therefore, one can get here this is r is equal to 0 to pi by 2. So, here we will get one will get here is equal to pi by 2 here, r is equal to 0, e is equal to 0 pi by 2 here I wrote here, and therefore, one will get something like this. This is the value that we will get, and so this is the way it comes out to be. And so, here at r is equal to a, okay, it comes out to be, therefore, will come out to be equal to 1, E1 is equal to 1 that I showed, and so at r is equal to a, okay, this value comes out to be like this. So, at the edge and at the side this is different, and it is profile of an this is the profile of an indenter that will give rise to this kind of uniform load on this surface. So, one can also find out the mean displacement in the loaded surface, and I will request you to verify this particular result. Now, one can also get the tangential displacement at B due to the differential load at C, and this will be given by this. Now, here I will explain it in the next lecture that how to get the tangential displacement. Yeah, I will stop here for today, and I will take up the next derivation in the next class, and thank you for your kind attention.